in physics 是3个美国人，他们所做的工作是在叫做高能物理或者基本粒子物理。他们的工作当然是很重要的，所以是值得的。不过就是我已经跟大家讲过了，基本粒子物理是在过去50年之间有了很重要的发展，可是 it's very unlikely that similar important developments will happen in the next 20, 30 or 40 years. As I told you repeatedly, the most likely developments fluctuate very rapidly in physics. So for your generation, if you go into high energy physics or elementary particle physics, the possibility of you making a very important contribution is not very large. It's at different periods. The prospects are different. When I was a graduate student, the prospects was good because that field was young, was the beginning. Now that field is old and it has many difficulties. So the experiments that are important in experimental high energy physics cost billions of dollars. As a consequence, there are very few experiments. But in contrast, 2 weeks ago, a very exciting new experiment was done by a professor named Moses Chen. 他姓陈，他是香港新界长大的， and he got his PhD in Cornell. His field is low temperature physics. In particular, he specialized in helium at low temperatures of approximately 2 degrees Kelvin become a superfluid, and that has been known since the 1930s. It's a beautiful subject. What he found now is that if you go to lower temperature and go to about 60 atmospheres pressure, it becomes a solid. That was also known before, namely that under pressure in low temperatures, liquid helium becomes a crystal. That has been known for a long time. What he found that's new is that that solid also has a superfluid component in it, and that was not known before. So he published this paper, and I'm sure he will be nominated for a Nobel Prize very soon. We have invited him to come to Tsinghua to give a lecture, and he will give 3 lectures next June. So at that time, perhaps you could listen to the lecture. I hope I can convince him to come to become a faculty member of Tsinghua. His experiment does not require a whole 研究所. His experiment can be done maybe with 1 person and 1 graduate student. So that's the kind of experiment which China should try to concentrate on, because it's easier to have great success. Okay, now we'll go to what we discussed last time. we were talking about a harmonic motion. If we have a spring, the block would oscillate, and the equation is mx double dot minus kx. We oftentimes write it this way: x double dot equal to minus omega squared x, where omega squared is equal to k over m. And the solution of this is a cosine x. If you take the cosine omega x, if you take cosine omega x and differentiate it twice, you get omega squared with a minus sign. But sine omega x is also a solution, and because the equation is linear, so a sum of the two is also a solution. But you can also write this as c times cosine, because cosine of a sum is equal to a cosine plus a sine. And of course, these are all equivalent forms, and you can write as d sine. Such motion is called harmonic. An important thing is that small oscillations are all approximately harmonic. 为什么呢？ Because 假如这个 force 不是 minus kx， 我们可以 try to expand the power series. So for example, plus alpha x squared plus beta x cubed plus etc. The force may have a linear term, and then we have a quadratic term and a cubic term. But if the oscillation is very small, the quadratic and cubic terms, if x is very small, the quadratic and the cubic terms are going to be much smaller than the linear term. So therefore, it becomes approximately harmonic. That means only this term is important. So all small oscillations are approximately harmonic. So that's why harmonic motion is extremely important. In fact, at the beginning of the 20th century, quantum mechanics was developed. How was it developed? First, people knew that there was some problem with classical mechanics. I already mentioned that people did not understand why an electron going around the nucleus would not continually radiate. And if it does radiate, it would lose energy, and therefore it would go spiral into the nucleus, and then would combine with the nucleus. That means the atom would not be stable. So in the first 20 years of the 20th century, people knew that there was a problem. And gradually people learned that the mechanics has to be changed. And so the main problem at that time, one of the main problems, perhaps the most important main problem, was to find a new mechanics. And that was where Heisenberg as a young man, made a breakthrough. He later wrote that he had the hay fever, 他是敏感. So he took a vacation in a small island in northern Germany, and there he began to work on the dynamics, new dynamics of the harmonic oscillator. That's one that we are talking about. And there he found the clue to a new dynamics, and that later became quantum mechanics. However, he did not know enough mathematics, so he wrote a paper about the harmonic motion using the new dynamics. That paper is now called the one-man paper. It was published under his name. He left that paper with his, he was a postdoc, so he had a advisor. The advisor was Max Born, who was 15 years older than Heisenberg. So Max Born took a look at it and recognized that there was something very important, namely the mathematics that Heisenberg was talking about was matrix mathematics. But Heisenberg didn't know matrices, so Heisenberg had very complicated equations which Born recognized as matrices. So Born, in Heisenberg's absence, Heisenberg went away to do something, and Born collaborated with another postdoc of his named Jordan, and they wrote a paper that was called the two-man paper now. And then when Heisenberg came back, the three of them wrote a three-man paper, and that the one-man paper, two-man paper, three-man paper founded quantum mechanics. So you see how the harmonic oscillator played a very important role in the history of physics. Now, what we just said is that any motion in some respects is, if the oscillation is very small, is approximately harmonic. But that is under the condition that this is a positive sign. What happens if it's negative? This is a negative sign. What happens if it's positive? One can construct such a mechanical system too. Does anybody know how to solve that equation? What after second derivatives comes back to itself? What you need is a quantity x as a function. Sorry, this should be t. It's harmonic with the time. What x as a function of t? After the trick here is you want to find an x. In this case, you want to find an x whose second derivative goes back to the original form with a coefficient. And we know it's a sine or a cosine, because a sine after you differentiate becomes minus cosine, and becomes cosine. Cosine you differentiate becomes minus sine. So therefore after two differentiations, it comes back to itself with a minus sign. Now we want something which comes back to itself without a minus sign. Does anybody know what that function is? maybe you have not learned enough calculus. It's in fact this case is simpler. It's the exponential function. If x is equal to exponential omega t, if I differentiate it, the exponential function after differentiation remains the same form. After you do it again, it remains again the same form. So if I take this, then x double dot is equal to omega squared exponential omega t. So you see, it therefore, if you again define k over m as omega squared, then this is a solution. But exponential minus omega t is also a solution, because each time you differentiate you get a minus omega, and the square of minus omega is omega squared. So another solution is a positive, is a negative exponential. So therefore the general solution is x is equal to a exponential omega t plus b exponential minus omega t. Each of them, after you differentiate twice, will give you omega squared times the original one. Because it's linear, so therefore you can linearly combine. Now, does anybody know what is the exponential omega t plus exponential minus omega t? That's called the hyperbolic cosine. So this can be written as c hyperbolic cosine of omega t plus delta. You can also write it as a d hyperbolic sine omega t plus delta. Exactly like that. The only thing is you change sine and cosine into hyperbolic sine and hyperbolic cosine. It's very convenient to familiarize yourself with the hyperbolic functions. Does anybody know why harmonic functions sine and cosine are so related to hyperbolic sine and hyperbolic cosine? That is because cosine x in fact is equal to 1/2 of exponential ix plus exponential minus ix, and sine of x is equal to I exponential ix minus exponential minus ix. So you see that the cosine and if you compare that with while cos of x is equal to exponential. So you see that these two are very similar, except that there's I in front of the x for the ordinary harmonic functions. There's also a similar formula here. Okay, now we go back to chapter 8. We have talked about the potential energy. We'll talk about two kinds of potential energy. So gravitational potential energy is equal to mgz. Z is upwards. We have talked about the spin potential energy. And that's equal to 1/2 kx squared. These are called conservative systems. In other words, the kinetic energy and the potential energy added is a constant. In the case of the spring, spring, when the spring is most compressed, the potential energy is high, the kinetic energy is 0. When it's most compressed, the block is not moving, so V is equal to 0, so the kinetic energy is equal to 0. So it's the minimum kinetic energy, maximum potential energy. When it goes to this other end, it again becomes minimum kinetic energy, maximum potential energy. In the middle, the potential energy is 0 because x is equal to 0, and the velocity is the highest, so the kinetic energy is highest. So therefore it oscillates between the kinetic and potential energy. But the sum of the two is a constant. That's why it's called a conservative system. And in a conservative system, if I plot the potential energy as a function of x, like 1/2 of kx squared is a parabola. And if the total energy is here, it oscillates between these 2 points. This is minimum kinetic energy, maximum potential energy, and at this point the kinetic energy is 0. The kinetic energy is always equal to this. So at these 2 points the kinetic energy is 0, and at this point the kinetic energy is the maximum. For a non-conservative system, for example, if this block is moving on a rough surface so that there is friction, if this block is moving back and forth but on a table with friction, then it will continue to lose energy. So the path would be like something like this. This is the potential energy. Its total energy would continuously be smaller, so it will go. What I'm plotting is the sum of the kinetic plus potential energy, and eventually it comes to stop here. What happens to the energy? Well, we'll come to this later. It becomes heat. The friction generates heat, and so the energy, the mechanical energy is lost, but the total energy is not lost. The mechanical energy is lost becomes the thermal energy. It becomes heat energy. That is a fundamental law of thermodynamics, which we'll come back later to. So in a case like this, it's a non-conservative system. Conservative or non-conservative, referring only to the mechanical part. The whole system we know is always conserved. In other words, the conservation of energy is universally true. But of course, you know that the total energy is conserved. That in a non-conservative system, the mechanical energy lost goes into heat. And if you add the heat energy to the mechanical energy, you get a constant. That was only understood in the middle of the 19th century. After that, it became an important fundamental law of physics. But at the beginning of the 20th century, as I told you, there were puzzles about why an electron does not continually spiral into the nucleus. And then there were other problems like radioactivity. So in the 1930s, Niels Bohr, who was one of the great physicists of the 20th century, advocated that in fact energy conservation is not universally true. That turned out to be a wrong suggestion. But I told you this only to show that at each moment, if there's a problem, one will have to find a way out. And one of the ways that one would look into is to see whether some fundamental laws of physics was defective. And that's why Niels Bohr proposed in the 1930s that the energy is not absolutely conserved. Now suppose at this level I have a slide. Suppose this height is h. Then the potential energy difference between here and here, when it goes from this point to this, it loses potential energy. The lost potential energy is equal to mgh. What happens if the slide looks different? If a child slides down this smooth slide, the potential energy difference is still the same thing. It's mgz. So in this case, it's mgh. In other words, the total potential energy difference is independent of the path. Whether it's this way or this way, the potential energy difference between the beginning and the end is the same. It's called path independence. Of potential energy. Anybody with any questions? Okay, now let us look at the potential energy curve. This is u of x, this is x, and the force is equal to minus du dx. We have this formula. So at every moment, the force on the particle is this. So the equation of motion is mx double dot is equal to minus du dx. So let us see what it means. The total energy is here. At this point, the kinetic energy is this distance. So at this point, there's no kinetic energy. That means it's not moving. Velocity is zero. At this point, du dx is negative. So minus du dx is positive. That means the force is positive. So that means that it pushes it in this direction. So it goes faster and faster, so the kinetic energy increases. At this point, the kinetic energy reaches a maximum, or a local maximum. But at this point, the slope is zero. That means the force is zero. So at that point, the particle is suffering no force at all. But it has a velocity which is going in a positive x direction, so it will move to the next point. At that point, the slope becomes positive, so the force becomes negative. That means, although it's still moving in the x direction, but it's suffering a force opposing it. Therefore, it slows down. And indeed, you see that it goes slower and slower until it reaches this point. At that point, the force is zero again because the slope is horizontal. After which, it increases again because the slope is negative and therefore the force is positive. So it begins to accelerate until this point where it has an even larger kinetic energy. And then it slows down again because it has a negative force until it reaches this point when the velocity becomes zero. And the slope is positive, so therefore the force is negative. That means it reaches a point where it's no longer moving, but it suffers a force pushing backwards, so therefore it begins to oscillate back. So therefore you see that it oscillates between these two. Now what I said in the last few minutes is very simple and it's very obvious, but go through it again in your mind, and so that whenever you see a diagram like this, you would immediately intuitively know the precise meaning of the motion and the force at each point. Now last time we talked about this curve, but I made a mistake. You may or may not remember. I was talking about a slide. Now let us, this is a potential energy curve. So this is a potential energy diagram. Now let us talk about a different problem. The different problem is that we have a slide. 一个滑梯. When I started on that part of the discussion last time, I had the wrong idea. Without having thought it through, I thought that this and this, because it looks similar, are the same problem, but it's not. So halfway through, I realized the mistake, so I asked you to scratch out what I said, and we started anew on this. Now let us go back to this and analyze this more in depth, so that we understand precisely where the mistake is. In this case, the total energy, for example, the total energy is equal to the potential energy. The potential energy is mgz. In this case, this is z. This is x. It's a slide. And this is the potential energy. The difference is the kinetic energy. The kinetic energy is 1/2 of mv squared. V consists of vx squared plus vy squared plus vz squared. Now what is the Vx? It's dx dt. This part is u of x. Z is a function of x plus 1/2 m dx dt squared times 1 plus dz So the mathematics of this problem is different from the mathematics of this problem in the potential energy curve. There is no such a term. In this case, the energy is equal to U of x plus 1/2 dx dt squared. So you look at these two, there's this term. And that's where, in the middle of my explanation last time, I realized that they are different. So I asked you to scratch out this. Any questions? There's on page 154, there's a checkpoint 5. Let's discuss that. It talks about a surface which has friction, and there's a block which is pushed with a force, and the table gives the book gives you several possibilities. If the force is 5 Newton, 7 Newton, and 8 Newton, it travels a certain distance, a fixed distance. It travels a distance d. A velocity. If you push it with a 5 Newton force, the velocity, the book says that the velocity decreases. If you push it with a 7 Newton force, the velocity is constant. If you push it with an 8 Newton force, the velocity increases. This is, of course, completely in agreement with our intuition. The block is on a frictional surface, so there is a frictional force. The frictional force, a kinetic frictional force, is equal to mu times the normal force. The normal force is fixed, is the weight of the block. Mu times that constant force, so it's a fixed number. That fixed number is the frictional force. So what is the frictional force? According to this table, the frictional force is 7 newtons. How do I know? Because if I push it with a 7 Newton force, it exactly cancels the frictional force. So therefore the velocity remains constant, no acceleration. So we know the frictional force in this case is 7 newtons. If I push it with only 5 Newton force, then the friction is stronger than my force. So therefore it slows down, so it saturates us. If I push it with 8 Newton force, my pushing is stronger than the friction. So therefore it would increase. So therefore it does. Now, how much energy do I spend in a distance of d? How much work do I do? In this case, it's a 5d. In this case, if it travels the same distance, so the work done. In this case, it's a 5d.
In this case is 7d. In this case is 8d. In this case I do more work than this case. In this case I do more work than this. What happens to that work? It becomes heat. So there's more heat generated in this case than this case. This case has more heat generated than this case. So it's a very elementary problem. Now let's try 51p. 51p talks about a block. A compressed block which originally V is equal to 0. So the spring would expand, and so it will go to these 4 points. This is where it's a natural. The spring comes to the natural position. From this point on, there's going to be friction. So this part of the table has friction. Before that, it's assumed that there is no friction. So this first part has no friction. And in this frictional surface, it moves this distance. It moves a distance L. L is equal to 7.8 meters. It moves 7.8 meters along a frictional surface, and the mu kinetic is equal to 0.25. The spring constant is equal to 640 newtons per meter. The mass is equal to 3.5 kilograms. Now first, let's ask at this point the spring has a velocity. The velocity comes because originally there is a potential energy stored, no kinetic energy. Here there's no more potential energy for the spring, so all the energy becomes the velocity, and the energy there is equal to 1/2 mv squared. We don't know what v is at this moment. Now, during the latter part of the motion, what is the force? The force is equal to mu, which is known, times the normal force between the block and the table, and that's mg. But we also know this is equal to ma. A is negative, but we are talking about the magnitude of A. So we know the acceleration. Acceleration is mu g over m. No m. It's equal to mu g. So we have a block which is negatively accelerated, and it comes to a stop. Now I want you to remember for motions with constant acceleration,
there are two formulas which involve T. V is equal to V0 plus AT. The other formula that's important is distance is equal to the x is equal to x0 plus the V0t plus 1/2 AT squared. These two formula involving T you should always remember. But there's another formula which is very important which doesn't involve T, and that tells you the kinetic energy difference. So it's a V, and this formula, V squared minus V0 squared is equal to 2AS. The final velocity squared minus the initial velocity squared is equal to 2A times the distance traveled. You can have various ways of remembering this, but anyway, this is a very important, very useful formula. It of course can be derived from those two equations involving T, which are more fundamental in some sense. Okay, let's apply that to this. So, one shouldn't say it's V squared minus V0 squared. The larger V squared minus the smaller V squared is equal to 2AS, where A is the absolute value of the acceleration and S is the distance traveled. So now, at this point, the velocity is 0. So we have a V squared is equal to 2 times A is equal to mu G, S equal to L. And the problem requires you to calculate the energy, and the energy is equal to 1/2 mv squared is equal to 1/2 m2 mu GL. So this is A. B asks you for the A and B have the same answer. Now that we know the final velocity, C asks you how much smooth surface did the spring travel. You just equate the energy, the final energy of the smooth motion part, the final energy, the kinetic energy plus 0. That's equal to the total energy. Is equal to the initial the kinetic energy is 0. The potential energy is 1/2 k times the distance squared. We call that distance from here to here, that distance d. So knowing all these quantities, you can calculate d. So d is equal to mv squared over k. And since v already is known, so this is known. Okay, let's try that. There are some somewhat tricky questions. Let's go to 54P. It's a mass of 40 kilograms.
pushing up a surface where the kinetic friction is 0.30. Now, if you resolve the force, the gravitational force consists of a component which is perpendicular to the surface and a component which is parallel to the surface. That's one of the forces. The other force is the reaction. Since there's no acceleration perpendicular to the surface, so the two forces perpendicular to the surface must balance. So R has to be equal to, this is mg, this is mg, this angle is 30 degrees, right? Yes. So this is mg cosine 30 degrees, and this is mg sine 30 degrees. So R has to be equal to mg cosine 30 degrees. What is the force, the component of force on block parallel to the surface? It has two components. One is the gravitational force component, so it's mg sine 30 degrees. That's downwards, so minus. And it has another component which is the frictional force. The frictional force is equal to mu times mg times mg cosine 30 degrees. Mg 30 degrees is the R. According to the frictional law, you multiply that by mu, you get the frictional force. And that frictional force is downwards. And that is equal to the acceleration. So the acceleration is equal to minus g sine 30 degrees minus mu g cosine 30 degrees. If the original velocity is v, if it's pushed up a distance d and stops, we use that formula, v squared minus v0 squared is equal to 2as. So therefore we get v squared minus 0 squared is equal to 2 times this number times the distance. Which is equal to 2g sine 30 degrees is 1/2 plus mu cosine 30 degrees is 1/2 of square root of 3 times d. If you know the velocity, you know the energy. I assigned quite a few exercises from this chapter. Some of them are very interesting. Let's try one more. This talks about the arrangement where these two parts are smooth, no friction. This part has friction. The friction has a coefficient of 2.0, or 0.20, sorry. It has a length of L, and H is equal to half of L. So this particle starts from this point, it slides down this smooth surface. So at this point it has a certain velocity. Let's call that V1. And after that it is slowed down because there is a friction on this surface. And it will have a V2 here. And then it slides to go up here and then come down again. Now, if the velocity is V2 forward, after it comes up and slide back down again, its velocity would be going the other way. What is the magnitude of this new velocity? Does anyone know what should be the new velocity? Is it going to be more or less than the original velocity? Come on, somebody must answer this. Let me repeat. Here's a particle with velocity V2 positive, and it goes up and it reaches, it's gradually being slowed down until its velocity is 0. Then it reverses itself and comes back to this point, at which point of course it's traveling the other way. If the original velocity is V2, what is the velocity after it comes back? It has to be also V2, only change sign. How do you know it's the same? Because of conservation of energy. The original energy is 1/2 mv2 squared. Finally the energy has to be the same because total energy is conserved. The potential energy of course is not changed because Z is the same. So the total kinetic energy at that point, whether it's going this way or this way, has to be the same. And therefore V2, it just changes sign. Okay, so then it comes back to this point, and then it gets slowed down, and then it climbs up with this, and comes back again, and so on and so forth. It goes back and forth. The problem first asks you, well, eventually it has to stop down, because every time it goes through the frictional surface, it would be slowed down. The question is, where does it stop? Okay, let's try this one. The first, the original energy, the original kinetic and mechanical energy, that means potential plus kinetic, is equal to mgh. And that's equal to 1/2 of mv1 squared. Right? Because the difference of the potential energy between these two is mgh, and that is completely converted to kinetic energy. So it's 1/2 mv squared. So therefore we know v1 squared is equal to 2gh. Now what is the force? What is the acceleration in this friction part? The normal force is mg. So that's the first part. The normal force is mg, multiply that by mu. That is the acceleration. The acceleration is equal to minus this quantity. Therefore, A is equal to minus mu g. We do not know whether it would stop in the middle. Here we have a particle with velocity v1. It travels along this frictional surface with a velocity, with an acceleration of minus mu g. So let us forget about this configuration and just ask this question. A particle with velocity v1 here, traveling along a surface with mu equal to this, and eventually, forget about this is infinitely long. We imagine it's infinitely long, and ask where does it stop? So eventually it will stop. If it's an infinite long frictional surface, it will stop somewhere. Where? Okay. So let this distance be called d. Then the velocity here squared, v1 squared, minus the velocity here squared is equal to 2 times A, which is mu g, times d. So what is this? So we get d is equal to v1 squared over 2 mu g, which is 2gh divided by 2 mu g, which is equal to g over mu, which is equal to h over mu. Now mu is 0.20, so 1 over mu is 5, so it's 5h. H is equal to 5 over 2L. So that means that if it goes along this way, it will travel a distance equal to 5 over 2L. That is larger than L. We just computed it. So what does that mean? That means that the V1 in traveling along here, when it reaches this point, it has not stopped yet. What I just have done here is merely to test whether it stops before it reaches that point. But we have proven that left alone it will continue to go a distance of 5/2 L, which is much longer than L. So therefore it stops at this point. And not stop there. So now let's ask what is V2. So we have V1 squared minus V2 squared is equal to 2 times A, which is mu g, times the distance. The distance is L. So we know what is V2. V2 squared is equal to V1 squared minus 2 mu g L. Now, V1 squared is 2gh minus 2 mu gl 2 mu gl. That's equal to gl minus 2 minus 0.4 gl. So that's equal to 0.6 gl. So at this point, it still has a velocity. If you didn't do this, if you didn't do that analysis that we tried, namely assuming that it goes along without going up, it would go a distance of 5-2. If indeed you immediately try this, you would get this velocity. But if it stops in the middle, if the problem were such that it stopped in the middle, at this point you would get a V2 squared which is negative. That means that it does not travel the whole L. So you don't have to do this analysis which I just did. By just directly going to here and calculate the V2 squared, if it comes up positive, you know that it reaches the end. If it comes to negative, you know it has stopped in the middle. Okay, now it will climb up here, and it comes back, and it comes back with the same velocity, only reverse direction as we said before. And then you do this back and forth, eventually you would get the result. I will not go through with this. The conclusion is that it comes here, it climbs up this, it comes up here, climbs again, then it comes back again, and stops in the middle of the track. Follow this through. I'm not going to go to the end, but follow what I just said through. It's a very interesting exercise. Okay, now let's try another one. This one is also a little bit tricky. It has a slide which is 5r in height. At this point, it goes into a circle. Of radius r. So the particle slides down the slide, and it goes very fast at the bottom, and then it goes up. So first, what they want to ask is what is the velocity? What happens to the particle at this point? First, we do not yet know whether it will reach this point, but let us assume that it does reach that point, because it might have fallen off the slide. Suppose suppose it does reach this point, then 1/2 of mv squared has to be equal to the potential energy which has been lost. The total height is 5r. The slide from this circle from here to here is 2r. So therefore 3r is the kinetic energy, the potential energy loss. So 3 mg times r. mg times 3r is the potential energy lost. That is equal to the kinetic energy. So therefore we know what is v squared. Is 6gr. Now at this point, let us analyze its force. At this point, here we have to let this point be called A. The force on the particle consists of two terms. One is the reaction. One is mg, the gravitational force. The other is the reaction. It's supposed to be a smooth. It's supposed to be a smooth slide. So there is no horizontal component of the reaction force. So there's only two forces, R and mg. Both of them are downwards. R plus mg is equal to the total force. Now here we have to use a formula that we derived twice a few times back. If you have a particle going through a motion which is not necessarily uniform, but it's circular. It's a circular motion, non-uniform. We had a formula about that acceleration. And the acceleration in the perpendicular direction is equal to v squared over r, independently of whether it's uniform or not. So this force has to equal to mass this force has equal to mass times the v squared over r. Let me repeat. For a non-uniform circular motion, the acceleration along the radial direction is v squared over r, independently of whether it's uniform or not. That statement is implied in the formula that we had derived several times. So now we can calculate the r. So r is equal to minus mg plus m v squared over r. V squared is 6gr, so it's equal to minus mg plus m 6g. And then therefore it's equal to 5 mg. The most important thing here is that this is a positive. Why is that important? Well, just use your intuition. If you were in the amusement park, 这在娱乐场有这种东西的，你从上面滑下来，然后到这儿它可以转一圈。假如你做过这个的话，你到那个点上面的话， 假如那个的 reaction 是个这个 R 是向下的，是 positive 的话，那就是代表那个 track 把你向下 push。那换句话就是你 push 那个 track 向上，那时候你心里头很踏实。假如那个数目变成0的话，那时候你就心里头就着急了，因为你要掉下来的。所以这个 R 大于0是非常重要的一件事情，这就是证明说是这个东西它还要继续走下去。好，这是它这个题目。不过我们现在把这题目稍微改一改，我们说从另外一个 height 上滑下来要发生什么现象？ What happens if h 是 less than 5r？ 比如说是 if h is equal to nr， 刚才 n 等于5。好，这其实你用不着算你就知道，假如这个 h假如这个 h 是在这儿，是跟这个假如这个 h 是在跟这个圆心在同一个 level， 那你当然知道，你用不着算你就知道，你从这滑下来以后，它就 reach 到这点就停了。为什么呢？因为这点的 potential energy， 这两点的 potential energy 就是一样，所以这点的 velocity 等于0，这点 velocity 等于0，有时候就滑回来，所以它就这样转。所以这代表 n 等于1，这是 n 等于1的时候。所以 n 小于1，我完全知道怎么回事情。它 n 小于1的话呢，就是代表它从这种地方，那它就换来换去。所以 if n 是小于1的话 oscillates， 这大家都同意吧？这不是 harmonic， but nevertheless oscillate。为什么不是 harmonic？ 因为这边，因为这个 surface 可以是很稀奇的样子，就是中间不能拱，你不能这样，你中间这样一下，那当然不行了，它不能走过这叫 barrier， 不能走过那个，所以 n 小于1没问题了。所以现在问题有意思的就是 n 大于1，n 大于1了以后，那么它从这滑下来的话呢，假如只讨论它的 energy 的话呢，它可以 reach 这一点。可是你可以想象到，它绝对不会那样子的，因为它还没到那一点的话，它就掉下来了。所以呢，对 n 大于1，n 不太大的时候是最有意思的问题。所以咱们来研究研究这发生什么问题。我们还到刚才那样子，那么它到这点的时候，它的kinetic energy， 它的 potential energy lost 是 n 减2 m g r， 它从这个距离是 n r， 所以这一点到这一点之间的 difference 呢是 n 减2个 r， 所以这是它的 kinetic energy。所以 v square 呢是等于 2n 减2 r g r， 所以 v square over r 就跟刚才一样的办算 v square over r 呢是等于 2n 减4 g。那么到刚才一样算法呢 mg r 加上 mg 要等于 m 乘上这个，所以 r 呢是 是等于 mg 2n 减4减1等于 mg 2n 减5。所以假如 2n 减5是大于0的话就没问题。R 就是大于0，那你转到那上头你很踏实，所以没问题。那这就代表是 n 是 2.5， 所以在很显然 n 在 2.5 以上就都没问题。可是在 n 在 2.5 以下怎么样呢？这得重新研究。我们现在来翻译，要来研究一下，在这点，这个角是西塔，西塔小于90度的时候，它还没有到这儿，西塔大于90度就是跑到上面去了。我们这个西塔算的时候，好像是西塔小于90度，不过大家知道这个算学的妙的地方，就是你如果算对了的话，那个结果在小于90度、大于90度都是一样的。所以咱们现在就来这个。那么我现在要问到这一点的时候，它这个 R 是什么？那么第一，在这一点呢，它的这个 kinetic energy 是什么呢？它从上面掉下来是 nr 减掉于 r， 是从顶上到这个圆心的距离，加上这一段是 r cosine theta。N2 减 2是从顶上到圆心的高度的 loss， 再加上这一段，所以这个是整个的 distance， 这个 quantity 乘上 mg 是 total potential energy lost， 这要等于1/2 mv squared， 所以 v squared 就知道了，等于 2g R 乘上 n 减1加 cosine theta， 所以 v square over r 呢是等于 2g n 减1加上 cosine theta。我们现在是在 n 大于1。我们现在这个 n 小于1，我们刚才已经讲过了，它在 oscillate， 所以现在我们研究是在 n 等于1跟 2.5 之间。那么这个 velocity 知道了以后呢，我们来算这个 force， 这 force 还是跟刚才一样了，这 reaction 是这个方向的 reaction 减掉reaction 加上，我看它有个 force 是这样的，这个 force 这一段，这是 theta， 所以这是 mg， 所以 mg cosine theta。mg cosine theta 是像这样的，这个是 r， 所以说 r 减掉这个，这要等于 acceleration 乘这个，又用刚才我讲的 non-uniform circular motion， 所以这是 2mg n 减1 加上 cosine 西塔，所以 R 等于什么呢 ？R 等于 mg 2n 减2加上2个 cosine 西塔加上 cosine 西塔，所以等于 mg 乘上 2n 减2加上3个 cosine 西塔。这个方面呢，虽然我们在画的时候是这个西塔是小于90度，可是它也对，当西塔大于90度，西塔大于90度，什么时候要掉下来呢？这个 R 等于0的时候，就是我刚才说你要做那边做得上的，你忽然觉得你对那个 track 不加压力了，你就知道就危险了，你就掉下来了。所以呢 ，R 等于0是这个掉下来的地方。那 R 等于0就是什么？就是这个是等于0，所以就得出来了 cosine 西塔是等于1/3 2个1减 n。比如说 n 等于5/2的时候 cosine 西塔，这个 cosine 西塔是掉下来的那个你人要掉下来的那个 cosine 西塔就等于这是负的，这是-1，所以西塔等于180度。所以如果 n 等于5/2的时候，它转到这个180度的地方，它就掉下来了。假如是 n 等于比如说是3/2，那 cosine 西塔是等于负的1/3，那这西塔等于差不多110度。所以就是它这样转上去，过了90度，稍微再过20度的样子，在那就掉下来了。假如在西塔等于1的时候 ，cosine 西塔等于0，西塔等于90度。在这情形之下，它那个东西是横着的，所以你到那儿就，它其实就掉回来了。OK， 底下我要换一个 chapter 了，我们要搞到 next chapter 9。我想今天我不讲了。上2个礼拜以前有几位同学送我花的时候，我答应了，说是我给2个演讲。现在我跟这个就是课外的演讲，可是只限于给各位同学。现在我想是这样。我们是11月1号有期中考试，在期中考试以后，连着2个礼拜，我就给你们120个人，做2个半通俗的演讲吧。至于说这个时间是在周末还是在晚上，这2位教授会跟我商量去研究，希望跟你们的上课时间不冲突。OK， 拜拜。